Well, hello. Today we're going to be talking about tree diagrams and something called the counting principle. The counting principle is something that we probably addressed in a previous lesson somewhere, but we're going to kind of bring it all together here. Um, Tree diagrams are really nice. They're actually very powerful. You can use them in some pretty high-level math, but they can get a little bit complicated as well. So we're going to look at just how to make tree diagrams and discuss counting principle. So the first thing to talk about is the counting principle. We're just going to multiply the total number of outcomes for two or more experiments to get the total number of distinct outcomes. Now, once we get to some examples, that'll probably make a little bit more sense, but you could think of this like one of the examples we're going to be looking at is flipping a coin and rolling a die. Like, how many possible outcomes are there? Well, we can use the counting principle. A sample space is a list of all possible outcomes from an experiment. A sample point is just one of those outcomes. And a tree diagram is just a picture that shows the possible paths that you could take through the course of your experiment. Now, you've probably all drawn a tree diagram at some point in your life, so it shouldn't be totally new, but we're going to see how these are connected to each other. So the first thing we're going to look at is this idea of flipping a coin and rolling a die. I chose these two because these are some very simple examples that most people understand just fine. Now, the counting principle is very easy to do. How many possibilities are there when we flip a coin? How many possible outcomes are there? There's two. How many possible outcomes are there when we roll a die? There's six. Well, the counting principle says that we're just going to take the number of events that you have, or the number of outcomes for each of these, and we're just going to multiply them. 2 times 6 equals 12. We should end up with 12 possible outcomes in our sample space. Now, let's take a look at a tree diagram and what that might look like. So, first thing I could do is I could flip my coin, and when I flip my coin, I could either get heads or I could get tails, right? And then after I flip my coin, I'm going to roll the die, and I could either get a 1, or I could get a 2, or 3. I could also possibly get a 4, a 5, or a 6. I know that's okay. So we've got all that. Those are all the possible ways that I could roll a die. Now, when I roll the coin with tails, or sorry, roll the coin. When I flip a coin and if it comes up tails, guess what? I'm going to get those same possible outcomes here because when you roll the die, you're only going to get 6 possible outcomes. The numbers 1, 2, 3, 4, 5, or 6. Now, if you follow the path of each one of these, right? That's what it means when we say it's a picture representing the path here. We could get, if we go this way, we get H1, right? That's just saying that H1, heads and then rolling a 1 is one of your outcomes. Or we could follow this path and get heads and then a 2. So I could get H2, I could get H3, H4, H5, H6. I could get tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Okay. All right. So these are all the possible outcomes. So here's what we got. We have our counting principle here that tells us the number of outcomes. We know there's going to be 12. Here we have a tree diagram illustrating all 12 possible outcomes. And then over here, I actually have the sample space. Let me clean this H up a little bit. So our sample space is a list of all possible outcomes. H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. That's our sample space. And then if I were to choose one of these, maybe this one right here, that would be a sample point. Okay? All right, let's move on now and take a look at another example involving some lunch. At a restaurant, each lunch special consists of a sandwich, a beverage, and a dessert. The sandwich choices are roast beef. We'll just let a little R represent roast beef. We could have ham. The beverage choices are coffee, tea, or sodas. And then the dessert choices are either ice cream or apple pie. Determine the number of different lunch specials. So when we go through and we talk about our number of lunch specials, we have our sandwiches, we have our drinks, and we have our desserts. And then we just got to figure out how many of each of those we have. Well, for the sandwiches, we have 2 of them. For the drinks, we have 3 choices, coffee, tea, or soda. And then for the dessert choices, we only have 2, ice cream or apple pie. And so in order to figure out the total possible number of lunch combinations, which doesn't really seem like it's all that much, it's only 2 sandwiches, a couple drinks, and desserts. But, that's actually, when you multiply all those out, you actually get 12. I don't know why I was going to say 16. That's weird. 12 possible lunch combos. And if you were to add on one more sandwich, right, we would have a lot more, right? Then it would be 3 times 3 times 2, or 18. Just by adding one more sandwich, we went from 12 lunches up to 18 lunches, right? Or if we were to add a different drink, maybe instead of coffee, tea, soda, or bottled water, I guess, right? Because if we did that, then we'd have 2 times 4 times 2, which would be 16. So just adding one more thing actually makes quite a few more possibilities. Now, if we were going to make a tree diagram for this, though, I'm going to start out with either roast beef or ham. Roast beef and ham. Then, after that, we're going to go coffee, tea, or soda, right? So we have coffee, tea, and soda. And then same thing here, coffee, tea, and soda. Then lastly, we have our desserts, and our desserts are either ice cream or pie, and we get that for each one of these, right? Ice cream or pie, ice cream or pie. IP. P. Ice cream or pie, ice cream or pie, ice cream or pie. Okay, we have successfully created a tree diagram. Then the next thing that you could do, if you wanted to, is you could go through and write out your sample space, right? We have RCI, we have RCP, we have RTI, RTP, RSI, RSP. It's funny, as I go through and do all these, we have so many acronyms in our lives. I feel like I have an acronym for like every one of these, like RTI is a response to intervention. It's a thing we do in education. RSI, that's the relative strength index whenever you're talking about trading stocks. Right, there's a lot of stuff here. Okay, HCI, HCP, HTI, HTP, HSI, HSP. So this is a list of all the possible lunch combos that we could have. Now let's go through. Now that we have our list, we have our sample space. And you don't always make a sample space, but if you're making a tree diagram, that is what you're doing. You don't have to always do it this way. If we had 6 sandwiches and 12 drinks, man, no way I want to make a tree diagram for that. Okay? But these relatively small ones aren't so bad. If a customer selects a lunch special, determine the probability that both a roast beef sandwich and ice cream. So that means we are looking for ones that are both R and I in them. Okay, R and I. They've got to have both of them, and those are the ones that we're looking for. So let's see. Roast beef and ice cream, yes. Roast beef and no. Roast beef ice cream, yes. No. Roast beef ice cream, yes. No. And of course, none of those will, right? So that means that we have 3 combos that have a roast beef and ice cream in them. So 3 the probability, 3 out of 12. Okay, so the probability of roast beef and ice cream is equal to 3 out of 12. Of course, we would reduce that down to 1/4 or 0.25. Now for the last one, find the probability that neither tea nor apple pie, so no tea, no pie. That's what we're looking for this time. Let me clear these other ones out so we don't get confused with them. Okay. No tea, no pie. Those are the ones we want this time. Let's see. No pie, no tea. Yep, we're good. Oh, that one has pie, tea, tea. We don't want those. Oh, there's good. And then this one has pie. Okay, so let's move down here to the bottom one. No tea, no pie. Ice cream, coffee. Yep, check. Oh, there's pie. Oh, there's tea. There's tea. There's tea and pie. That's doubly bad, right? Here's ice cream and soda, and there's pie. Okay, so when we go through, we look at them this time now, all the ones that have check marks have no tea and no pie in them. Those are the ones we were looking for, and it looks like there's 4 of them. So we would come down here and we would say the probability that neither tea nor pie are selected would be 4 out of 12, or 1/3, or 0.3 repeating, or probably okay if you just put about 0.33. So all of those would be just fine, about 33%. Okay, so that's a tree diagram, and that's how we can use a tree diagram to calculate some probabilities. This would be pretty tough to do without a tree diagram. It's not impossible, but the tree diagram does make it a little bit easier if you take the time to actually make it. In probabilities, we have something called with replacement and without replacement. With replacement means that whatever it is, you're going to put it back and it can be selected again. Things that happen with replacement are like if you were to draw a card from a deck of cards, you look at it and then you put it back in, like it would be possible to draw that same card again. Another thing that you might not think about as with replacement is tossing a coin or rolling a die. And that's because if you flip a coin and you get heads, you know that when you flip a coin again, it's possible you could get heads. Or if you roll a 6, it's possible to roll a 6 again and again and again. So those are all with replacement, and it's very important to distinguish whether or not that's allowed. For the other one, without replacement, means that once the item is picked, you cannot pick it again. Let's go back to our example with cards. Let's say you were drawing a card and you looked at your card and you have the Ace of Hearts, and you hold that card in your hand and you reach back into the deck with your other hand and you try to take another card. Well, it would be impossible for you to draw that Ace of Hearts again because you already have it in your left hand. You're reaching back into the deck with your right hand. So like you couldn't get it again. That would be without replacement. And when you do stuff without replacement, the probability changes each time depending on what you're doing. Okay, so we'll look at an example of that. Your TV remote has some buttons for digits 0 through 9. And if you're going to press 2 buttons, okay, notice here that this is 2. We'll come back and do one with 3 here in a second. How many numbers are possible if the same button could be pressed twice? Well, when I go to push the first button, right here, this represents both button pushes. If I have 0 through 9, that's actually 10, right? Because you have 1 through 9 along with 0. So you have 10 different buttons you could push on your first push. Then, if you can push them more than once, right? They may be pressed twice. That would just be 10 times 10. You could actually get 100 different channels, right? Now, what if the same button could not be pressed twice? Well, when you go to push the first button, you pick any number you want. Maybe say you push 6, okay? Well, you have all 10 choices to choose from, and then let's say you just push the number 6. When you go to push the second button, you're not allowed to push that same one again, right? Because it says they may not be pressed twice. So that means that 6 is off the table. You only got 9 choices now for your next button press. That means that if we do this without replacement, you could actually only reach 90 channels, right? Because it would be impossible to get to channel 55 or to channel 33 or to channel 77, 88, 99, 00. All those would be impossible if you're not allowed to push the button more than once. Let's go through and look at this though. What if you press the button, if you press 3 buttons with replacement? Okay, well, 1, 2, 3 blanks. Okay, so we have 10 buttons to choose from, and we're doing them with replacement, meaning you could push 333 or 727, right? You can use the same buttons more than once. That's just 10 times 10 times 10, or now we actually get to 1,000 channels. And then what if you press the 3 buttons without replacement? Same idea as what we were doing up here. You have 10 choices for the first button press, and once you pick it, you can't pick that button again, so you only get 9 choices on the second one. Then, once you pick that button, you only have 8 choices left. You can see we're removing a choice every single time. So when I multiply these, I like to think like 8 times 9 is 72, times 10 is 720. Look, we get quite a bit fewer channels. We have a lot less channels whenever when we do this without replacement. Okay. This one's a very similar idea. Go ahead and use the counting the counting principle to figure out the number of possible outcomes. Okay. So with replacement, you're going to be picking 2 dates out of a 365-day year. Okay, not leap year. Go ahead and figure out the number of possible outcomes here. Pause it, and then make sure that you can do this. So when we're doing these with replacement, we're selecting 2 days, and we have 365 times 365. Right? And so when you multiply that out, we get 133,225, I hope. When we do this without replacement, it means once we select a day, we cannot select that same day again. We would actually have 365 times 364, right? Because once you pick a day, you can't pick it again. So now this time, we actually have 132,860. We're going to look at an application to probability here, and this is kind of jumping ahead a little bit, but for other lessons. But I think this fits really nice for just giving you an example of where this replacement idea really does affect things. Find the probability that 3 queens are selected out of a deck of 52 cards when you're doing this with replacement. Okay, so you're going to draw a card. Now think about this. How many queens are there in that deck of cards? There are 4 queens out of 52 cards. Then, if we're doing this with replacement, we're going to look at it. We're going to say, oh, look, we got a queen of hearts. So we put that queen back, and we shuffle the deck, and we're going to say, okay, what's the probability now? Like, on our second draw, we get a queen. Well, you know what? There's still 4 queens, and there's still 52 cards in the deck. And we look at it, and we say, oh, look, we got a queen of clubs. Cool. We look at it, we put it back in the deck, and we shuffle it. And what's the probability of getting another queen? Well, there's still 4 queens left to choose from because we kept putting them back, and there's still 52 cards to choose from, right? And so when we multiply that out, on top we're going to end up getting 64, and then on bottom we get 140,608. Now you could reduce that down, by the way. You could say like this is actually just 1/13 times 1/13 times 1/13, and that gets you about 1 out of 2197. And if you were going to turn that into a decimal, it's not very good. It's not very likely at all. 0.0045. So this is the likelihood of drawing 3 queens in a row. Okay. And then there's some more decimals that go after that, by the way. Okay, now if we do these without replacement, right? 1 out of 2,000 if we did them with replacement. But look at how this is going to change when we do this without replacement. Okay, start with a brand new deck, shuffle it around a couple times, and we're going to first draw a queen out. The probability of drawing a queen on your first draw is 4 out of 52. Now you take that queen that you drew, let's just say the queen of hearts. We take that queen and we set it aside, or you hold it in your hand, you set it aside. You're going to reach back in the deck, and you got to ask yourself, how many queens are left for me to draw? Well, there's only 3 queens left now. And how many total cards were there? Because not just the queens changed, but the total cards changed. Now instead of 52 cards, there were only 51 cards in the deck. That's because you have that Queen of Hearts setting off to the side already. Now, you reach back into the deck, and let's say for the second draw, you drew out the Queen of Spades. Now you have the Queen of Hearts and the Queen of Spades setting off to the side. We're going to reach back in the deck. How many queens are left to choose from? There are 2 queens left. And how many cards are there? There's 50 cards left. Okay, so now when you multiply all this, and you could do some reducing, that's 1/13 and 1/17 and 1/25, I think is what that all comes down to. But I'm just going to multiply those real quick. And this is what we come out with. We end up with 1 out of 5,000 chance. See, when you're doing this without replacement, the likelihood of you drawing a queen each time, it goes down. So that makes it much more difficult to draw 3 queens without replacement. Look, this time we only have the probability is 1 out of over 5,000, right? So it comes out to 0.00018. It's even less, right? It's a lot less than it would if you were doing it with replacement. So we'll look more at these later on in our chapter when you get into different types of probabilities. But I wanted to throw that in here now so that you could see how this idea of with replacement and without replacement is connected to probability. All right, the last thing I want to talk about is this idea of at least one, or at least once. So at least once is opposite of never. I know that seems strange, weird. It seems weird because you think always is opposite of never. Well, in our probabilities, the ideas of at least once is the complement of never. The probability of never getting something versus getting it making it happen at least one time. Okay, so those two are complementary to each other. And we've discussed this idea of complementary quite a bit in previous lessons. It's just 1 minus the event. So the probability that an event happening at least once is equal to 1 minus the probability of never. Okay? So just a kind of a quick silly little example. You buy some flower packet seeds, and they say that the probability of not getting any red flowers is 2/7. What's the probability of getting at least 1 red flower from the seed packets? Well, all we're going to do is we would take 1 minus 2/7, and that would get us 5/7. So this is the idea of a complement. We just subtract them. At least once is the opposite of never. Okay? All right, so I hope this helps out a little bit with tree diagrams. That's what we were looking at today, tree diagrams, and then with and without replacement and counting principle. Good luck with your probabilities.